lecture series. My name is Emily Petroff, and I'm Perimeter's Associate Director for Strategic Partnerships, Grants, and Awards. I'm delighted to welcome you back to the Mike Lazaridis Theater of Ideas here at the Perimeter Institute in Waterloo. C'est un grand plaisir de vous accueillir ce soir à l'Institut Périmètre pour ce qui, nous sommes sûrs, sera une présentation fascinante. Perimeter Institute was created to be a gathering place where people can come together like we are doing tonight to ask the big questions about the universe and search for the big answers. Perimeter will soon celebrate 25 years of bringing people together from all paths, researchers, students, teachers, and the general public, to explore the fascinating world of physics. But people on this land have been asking big questions about the universe for thousands of years. The quest to understand the fundamental building blocks of nature, what we're made of, and where we come from is a human constant throughout the ages. We acknowledge that Perimeter is situated on the traditional territory of the Anishinaabe, Haudenosaunee, and Neutral peoples, and Perimeter rests on land a little less than 5 miles from the banks of the Grand River, which means that we are situated within the Haldeman Tract, the tract granted by the British to the 6 nations of the Grand River and the Mississaugas of the Credit First Nation. Nous saluons et remercions les divers peuples qui nous ont précédés et nous nous engageons à agir de manière responsable et collaborative pour faire avancer la quête de savoir pour le bien de tous. Et nous remercions les Anishinaabe, les Haudenosaunee et les Neutres pour leur accueil. We would like to take a moment to say thank you to the people who make events like these possible. Thank you to all of our supporters who help us to engage and inspire young minds, train and support educators, share science with the general public, and help bridge the knowledge gap in science. If you'd like to join our growing community of friends and supporters, please visit our website to learn more. For those watching the live webcast, please join the conversation online. We are at Perimeter on Twitter or X, and if you have a question for our speaker, you can ask it with the hashtag #PILive. So this week, Perimeter is hosting the 2nd annual SciComm Collider, a gathering where scientists, educators, and science communicators are coming together to learn from each other and find the best ways to communicate all the fun and wonder of science to a diverse range of audiences. They've been sharing their knowledge and enthusiasm on topics like crafting accurate analogies for complex topics, writing popular science books, and recording TikTok videos. So this conference has brought some big names in science communication to Perimeter, and it's been fun to see them in action so far. And now, it is my great pleasure to introduce one of those excellent science communicators and our speaker for tonight. So Dr. Clara Nellist is a particle physicist and science communicator with extensive experience in her field. She completed her PhD at the University of Manchester in the UK, where she focused on developing a novel pixel detector for the ATLAS experiment at CERN. She went on to work as a postdoctoral researcher at LAL, the Laboratoire de l'Accélérateur Linéaire in Orsay, France, where she continued her research, including analyzing the properties of the Higgs boson. Dr. Nellist moved to the University of Göttingen in Germany and then to Nijmegen in the Netherlands as an Excellence Initiative Fellow at Radboud University, where she also joined NICEF, the National Institute for Subatomic Physics in the Netherlands. Currently, she serves as an assistant professor at the University of Amsterdam and continues her affiliation with NICEF. Her research focuses on investigating the top quark with the ATLAS experiment, as well as exploring dark matter through machine learning algorithms. Dr. Nellist is also an active science communicator, which is what brings her to Perimeter this week. She's an advocate for diversity, equity, and inclusion in STEM, and engages with audiences on various social media platforms, including TikTok, Instagram, and YouTube. Tonight, she will tell us about the world of particle physics and the Large Hadron Collider at CERN. Please join me in welcoming to the stage Dr. Clara Nellist.
So thank you very much for that very kind introduction, and I'm very excited to be here this evening because I get to tell you about my favorite subject, which is the Large Hadron Collider at CERN. I want to make one disclaimer before we start, though, because this is very much an experimentalist's perspective. So I'm not a theorist. I spend most of my time either in the lab or at a computer analyzing data, and yeah, it's my pleasure to talk to you about the experiments that we have at CERN. So this is CERN. It's in Switzerland, and today we're going to take a bit of a virtual journey. Unfortunately, despite what people say online, we haven't actually invented portals yet, so we can't travel there directly, but we're going to virtually travel to Switzerland today and talk about the Large Hadron Collider. But before I talk directly about the experiment, I'm going to touch on the theory. So what are we actually looking for at CERN? Why did we build these giant experiments to study our universe? Well, oh, and also, this is one of the only equations in the whole talk, just to warn you. Right, so this is sort of a historical perspective of our universe. So experimentally, there's kind of two ways that we look at our universe. So either we build telescopes, and we send them out into space, and we look back in time by observing the universe as it was when it's very far away from us, or we can build accelerators like the Large Hadron Collider, and we can recreate the conditions similar to the early universe. So you might hear, for example, that the Large Hadron Collider is recreating the Big Bang. That's not true. We recreate conditions similar to fractions of a second after the Big Bang. So what are we looking for? So we have the standard model, and I would like to note that this is from the 2000s, so it's not complete. I mean, it's also not complete now, but there's something missing. But this is really our recipe book of the universe. So if you're familiar, for example, with the periodic table, it has some similarities with that. But we're looking even smaller into the fundamental constituents of our universe. So these are our particles. Some of them may be familiar to you. So for example, the electron is one of the first generation particles that we have in the standard model. Generations are these three. And over here we have the fermions. These are the particles of matter, so they are the stuff in our universe. And then we have the force bosons, so these are the ones over here. So for example, the photon might be familiar to you as the particle of light. And then we have the gluon, which holds atoms together in the structure of atoms together. And we have the W and Z bosons, without which our sun wouldn't shine. So this is our recipe book of the universe. And just to let you know, I'm not crying, but your trees are very enthusiastic at the moment, even though particle physics does make me emotional. So, as I said, there's some things missing from this standard model. So we don't have the Higgs boson. You may have heard a lot about that. So again, I remind you, this is the 2000s, so we're looking at before the Large Hadron Collider was running. So the Higgs boson isn't yet in this model. We don't have dark matter. I'm going to talk more about what that is. We don't know what dark energy is. And talking about the forces, we're missing a very important one. So we don't have gravity in this model. So these are our big questions, and so these are the four that I'm going to kind of discuss a little bit now. So the first one we're going to talk about is the Higgs boson, because this was discussed a lot for the construction of the Large Hadron Collider. And the aim of the Higgs boson, or more specifically the Higgs field, is to understand the origin of mass for elementary particles. So why does the electron have a mass? Why did some of the other particles have a mass? And what we think from our predictions is that in the very early universe, the sort of value of the Higgs field was 0, but it's not the most energetically favorable location for it to be in. So at some point, it fell down into this sort of well of potential, and it's off 0. So this is 0, and it's off to the side. So the Higgs field kind of prefers to be over here. And that gave mass then to particles. But, oh, and just a fun fact before we move on. If this happened very quickly, it might be something that caused ripples in space-time throughout the universe, in the very early universe. And so maybe if we build better gravitational wave detectors, which are being proposed, it could be something that we might be able to measure in the future, which would be very exciting to see ripples of the very early universe from this decay. But to kind of explain it better, and these are some videos of me skiing. Please don't judge me for my technique. I learned as an adult, so we don't have that much snow in the UK. So how do particles get their mass from interacting with the Higgs field? So for example, if you were a light particle, so first of all, the Higgs field is like a field of snow. And if you were a light particle, then it's like you're wearing skis on the snow. So you're kind of interacting with it a little bit. You are touching the snow, but you can glide over it. And this is, I apologize to the theorists in the audience, this isn't an analogy. So, but if you're a light particle, then you're gliding over the Higgs field, and so you have slight interaction with it, but you can move pretty easily through it. If you're a heavy particle like the top quark, which is the one that I study, then it's like you've lost your skis, and you've got to trudge through in ski boots. And so if you have a bit more mass, then you get stuck in the snow field, and then you've got to trudge through. And so more massive particles are like snow boots. And then the interesting one is the Higgs boson. So why was it so exciting that we discovered a Higgs boson? And that's because the Higgs boson is the excitation of the Higgs field, of the snow field. So if you find a massive ball of snow, that tells you that somewhere there is snow. And so by discovering the Higgs boson, it told us that the Higgs field existed. So that's why it was so exciting to be able to discover this particle. But the problem is, with the prediction, is that we didn't know what mass the particle was going to have. So often you hear about looking for a needle in a haystack, but searching for the Higgs boson was like looking for a needle in a stack of needles, and you've got trillions of them, and you're looking for one specific type, which was incredibly difficult, and you don't know what size it is. You don't know exactly the properties of the particle you're looking for. So this was all of the different predictions of how it could be produced in our experiment, and this was all the predictions of the different things it could change into depending on what the mass of the particle was. So it's very tricky then to be able to just look for one thing. You have to spread your net very wide to be able to discover this particle. And I'll come back to this a bit more when we talk specifically about the experiment. But there's also dark matter searching for new particles. So we know that, for example, all of the matter, all of the stuff that we see in our universe is only about 5%. And that the rest of it is dark matter and dark energy. And so we want to know what these things are. We want to understand what they're made of. And we know that dark matter exists in some form in our universe. We see its gravitational effects. So for example, if we have a galaxy and then there's dark matter in the way between us and the galaxy, we see the gravitational lensing, so the bending of the light as it travels towards us because of the mass of the dark matter. So we know that it exists, we just don't know what it is. The interesting thing, though, is we often talk about dark matter as this sort of one thing, but historically we've seen with particles, there was a whole bunch of them I showed you at the beginning of my slides. So it could be that it's not just one type of particle, but it could be a bunch of different things if it's a particle. Just to tell you my bias, I'm a particle physicist, so I'm going to assume it's a particle because I want to find it. So that makes it even more challenging to search for dark matter. And one of the really interesting theoretical proposals that was made was called supersymmetry. So this suggested that for all of the regular matter that we see down here, all of the fermions and the bosons, so all of the types of particles that we have, that they have partners that are potentially more massive and have different quantum properties. And this is a really nice theory. It explains a lot, and it could have a dark matter candidate. The problem is we've been looking for it, and so far there's been no evidence so far. So as an experimental physicist, the theories can be beautiful, but if I can't see them in my detector, then we have to move on. So it's not ruled out completely, but unfortunately it didn't show up as early as we thought it might. There's also a big question in our universe, where did all the antimatter go? So in the early universe, we believed that there were equal amounts of matter and antimatter. And when matter and antimatter meet, they annihilate. So if there were equal amounts, it should have all annihilated, and then we would just have a universe of light, which sounds very poetic and beautiful, but then we wouldn't exist. So fortunately, there was this ever so slight asymmetry between the matter and antimatter, but we don't understand why. We don't have a good explanation for it. And so as a physicist, I want to know why. It's one of the things that drives the work that I do. Also, this picture I love to show because it's the first photograph of antimatter, and it's just incredible that they could photograph it so early. And then there's also the strength of gravity, which is a big question. We think that gravity is quite a strong force. If I fall down the stairs, it's going to hurt a lot. I try not to do that. But I can overcome the entire force of gravity by picking objects up. So it's actually an incredibly weak force, and we don't understand why it's so weak. So some of the questions that we have about it, and these are very biased towards things at the LHC, is there a graviton? Is there a particle that's associated with gravity? We don't know. We haven't found it, but we do look for it. Are there extra dimensions that gravity is potentially leaking into? This one's trickier to answer, but there are a few proposals that if we find an associated particle, it could lead to some evidence that there's extra dimensions, but so far, nothing for that. And then a question I'm going to touch on near the end is, what is the strength of gravity for antimatter? So as a physicist, a question I get asked quite a lot is, when are we getting anti-gravity? When's my skateboard going to fly? And so this is a question that we also look at for the antimatter research. So how do we go about answering questions like these? What's the equipment that we use to answer them? So as I said, we're going to travel. So I'm going to take you to Switzerland. So this video is going to zoom in on Switzerland, where the Large Hadron Collider is constructed. So this is CERN. It's in Geneva, which is on the edge of the lake. Here you have the airport, so you can see just how big this is. And the Large Hadron Collider is a 27-kilometer long, about 16, 17-mile long particle accelerator. And we have 4 main detectors around the ring. I'm mostly going to talk about Atlas because it's the one I work on, and so I'm very biased, just to declare all of my biases. Excuse me. OK. So I really want to give a shout out to the accelerator complex, because I don't think we talk about this enough. You often hear of the Large Hadron Collider, but there's a whole series of accelerators that feed into this machine. And it also shows you the history of CERN. So for example, we have the proton synchrotron machine that was built in 1959, and we're still using it. It is still a useful machine. So at CERN, we never retire anything if we can help it. We build upon it, and we use it for our research. Also, I'm completely not going to have time to talk about this in the lecture, but there's other experiments at CERN, like Isolde, which is a nuclear facility, and it's studying atoms and sort of exotic atoms that can be created for very short periods of time. Super interesting research, but I can't touch on it today. OK, so let's whiz through some of these accelerators. And as the title of the talk says, it's from hydrogen to Higgs bosons. So we're going to start with the hydrogen. So we're going to zoom in now into the Large Hadron Collider facility. And I do actually want to pause. Oh, sorry, that's my screensaver. Great. So this is what I wanted to pause on, because we start with a bottle of hydrogen. And this bottle of hydrogen is literally about this big. So this is the source for the Large Hadron Collider. And a bottle of hydrogen, with the number of protons that are in it, could feed the LHC for 20,000 years. But we're not very careful about all of the connections, and we leak a bunch of the hydrogen. And there's lots of it in the universe, so we don't have to worry. So usually it's pretty abundant. So usually it lasts about 5 or 6 years, and then we replace it with a new bottle. It's also because we get rid of the beams quite often. So even though we fill the LHC, we often remove a lot of protons when it just doesn't become efficient to run them anymore. But we start with a bottle of hydrogen, and then, if I can get this video to play and pause in the right place, this is my favorite word in all of CERN. It's called the duoplasmatron, which is a pretty good science word. So what happens is we take those hydrogen atoms from the bottle, and actually, originally we used to strip the electrons away. What we actually do now is add extra electrons, so we have doubly charged hydrogen. Then we can focus them better, and then we strip the electrons away, and we're just left with the protons. So it's a nice engineering technique to make sure that those protons are really well bunched together, because that's what we need. We need a really concentrated beam of protons for our research. So let's press play again. So now we're going to whiz through. So we start with a linear accelerator that gets those protons up to some speed. Then we put them through the proton synchrotron booster. So we have 4 beam pipes for that. They get accelerated and then fed into the proton synchrotron, the PS. And they sort of start to become in a line. And then these get fed into the super proton synchrotron, so the SPS, where they go up to 450 GeV in energy. So they're starting to get close to the speed of light. And then they get sent into the Large Hadron Collider in opposite directions, and then we ramp up the energy of those particles. We ramp up the magnets, which are superconducting magnets, in order to keep those protons on the path. And then we collide them together in each of our 4 main experiments. So this already is a huge engineering feat. We have superconducting magnets that have to be kept at 1.9 Kelvin, which is 1.9 degrees above absolute zero. And all of this has to happen before they even collide. The next question you might have, but I'm going to answer either way, is why are we colliding protons? So we've talked a little bit about elementary particles. These are particles you can't break up into any smaller pieces, like electrons. So why are we not colliding electrons in the Large Hadron Collider? And the main answer is that electrons are very light, and they give off synchrotron radiation when they are sent around the ring. And so eventually they lose more energy than we can put in, and it just becomes technologically a waste of time to keep trying to speed them up. So protons are heavier, which means that we can get them to higher energies. But the problem is all the stuff inside of them, and I know Katie is very mad about the internal structure of the proton. So they're very messy. We've got quarks inside of there. We've got gluons. It's just a whole lot of stuff going on. And some of my colleagues compare it to like smashing 2 trash bags together. It's just you don't know which bit's going to collide. So it's very messy. But the benefit is we can go up to high energies, and we can explore a high range of masses. So we can go from about 50 GeV to 1 TeV, which is a big range of masses when we want to search for these new particles. So electrons are great for precision, but we want to go to higher energies. And we've gotten better at doing precision measurements with protons. So now we're going to look at arguably my favorite part, but again, biases, I worked on it. So we're going to look at the detector itself. So these are the 4 main experiments. We have ATLAS and CMS. These are what we call general purpose detectors. We take pictures of everything that comes from those collisions and then try and study what comes out of that. We have ALICE that was specifically designed for a different type of collision, so heavy ions. Instead of protons, we collide, for example, lead ions, which are more massive, and they create like a quark-gluon soup that is very similar to or we believe is very similar to the early universe. And so ALICE was specifically designed for this soup of quarks and gluons. And then LHCb is an interesting detector because it's quite one-sided, and LHCb focuses on this matter-antimatter question. It was really specifically designed to answer that. So we're going to zoom in to the ATLAS experiment. So this is the experiment that I work on. And as I said, it's like a giant camera. So these collisions are happening every 25 nanoseconds in the center of the detector. And then when the protons collide together, they create new particles that we haven't seen before. They exist in our universe, but we just don't have them lying around near us. But these particles don't last for very long, and they quickly change into other types of particles. And then this is that kind of firework shape you see from the center of the collision. So for example, Higgs bosons, we've never actually measured a Higgs boson. It always changes into other types of particles, and we have to measure those particles and work out that there was a Higgs boson there. So this is one of the big challenges that keep people like me busy, is doing all the reconstruction of these events. So we're going to look now at a sketch of my detector. I added this in just in case the little humans weren't big enough for you to understand the scale. This dinosaur is Sue from the New York Museum, so just in case you want to check my references for size, I did measure it carefully. But yeah, our detector is 44 meters long and 25 meters tall. So it's huge. It's a giant camera. And I'm not going to go quite through all of the different parts, but I left the labels in to show you that there's lots of different custom technology that goes into this detector in order to reconstruct the different types of particles that come from those collisions. So we are going to look a little bit at it, but it is a very complicated machine. So when we were building this detector, we started in 2002 with an empty cavern. So this cavern was dug 100 meters underground, which is where the Large Hadron Collider is. And then if you've ever had the hobby or seen anyone with the hobby of building a ship in a bottle, this was the challenge we had, because you can't build the whole detector above ground and then lower it down. You have to build it piece by piece and construct it inside the cavern, just like someone would do if they were building a ship in a bottle. So this is the first toroid magnet piece. There are 8 of these. They're hundreds of tons in weight, and they each had to be lowered in, and then we constructed the rest of the detector in place. So again, to give you a sense of the scale, this is a fisheye photograph. So I took a bunch of photographs and stitched them together to give you a sense of the size of the detector. And since I realize it's still quite a challenge to understand just how big it is, we're going to zoom in, and these are people. So it's a huge detector. And one more thing I want to point out before we move on to more specifics is I'm giving this talk today, but science is a team effort. So we have over 5,000 members in my collaboration alone from over 100 different nationalities. So it's really, to be able to do this kind of research, you need people from all over the world to come together to share our resources and to really tackle these big problems together. And I also pulled a bunch of photos from the different collaborations, and I would say this isn't even like 5% of my collaborations, like of my collaborators in different collaborations and in the accelerator team. So just to again get the sense of scale, there are 20,000 people that work at CERN or related to CERN. Okay, so now I want to tell you a little bit about how the detector works. So we've got 3 main parts for this detector. So now we're looking at the protons come in from this direction and also from this direction. So that's the beam pipe. They smash together like this, and then all of those particles are coming off in many directions. So in order to work out which particles have passed through our detector, it's a bit like looking at the individual fingerprints. So I'm going to start this running now, and we're going to have, I think we start with an electron. So an electron passes through the tracking detector, which looks for charge, and it deposits its energy in the calorimeter. And the calorimeter, you can think of the name for that as the like calories in your food, so it measures the energy of particles. And the protons pass through all of these and deposit their energy up here. The neutrons are neutral, so they don't get measured in our tracking detector, but they also deposit their energy up here. And the muons are the ones that make it all the way through to the edge of our detector, where we have a special section called the muon spectrometer. So muons are the heavier cousins of electrons, and they pass all the way through to the outside. And then the one particle that we know of so far that doesn't end up getting measured in our detector are the neutrinos. So these are incredibly light. They very rarely interact with anything. So we have to infer that they were there through the missing momentum in our detector. It's also one of the ways that we look for dark matter, because neutrinos are incredibly light, and one of the things we do know about dark matter is that it's massive, it interacts gravitationally. So if dark matter was being produced in our detector, it would have a similar signature to the neutrino, but with a lot more mass missing. So that's one of the ways that it could show up in our detector. One of the big challenges is that the accelerator teams that I told you about, when they concentrate those protons really tightly together, they do too good of a job. They're very good at their job, which makes it more challenging for us. So we have 600 million collisions per second, and these are then being read out by those different detectors, and only about 1 in a million are even interesting. So what we have to do is we've designed custom hardware and software in order to make very quick decisions about which of those particles, which of those events we want to keep. So about 1 in 10,000 events pass our first level of this data selection. So the hardware takes a very quick decision about whether or not it's interesting. And then it gets passed over to the sort of servers over here. And these servers save 1 in 1,000 event. So from 600 million to 1 in 1,000 is what we have to get down to. And this is just a limit on the data that we can process and that we can store, which is an incredible computing challenge. And we have a lot of people that are dedicated to the hardware and the software for this challenge. And then just a nice fact to add on, that data, once it's been selected from the second process, is sent to the CERN data center, which is on site. We call it tier 0. We have here it says 73,000 processing cores. And then this is sent out all the way across the world to be backed up in different sites around the world. And it means that people like me, when I want to access the data, I can work from here when I'm not in Amsterdam or I'm not at CERN. I can log into a computer anywhere, and I can access the data that I need, and I can study it from anywhere in the world. And it's also how we have so many international collaborators. So it is going to jump ahead and show you. So this is now the data getting sent around the world. But let's jump ahead. So now we're talking about, I've sort of been going through time a little bit. So now we're in 2008. And we had first beams in the LHC. So the LHC was constructed. You may have heard about this in the news, or maybe this you didn't hear about. But in 2008, we had the first beams in the LHC. And this got a whole room of scientists, in fact, not just this room of scientists, but scientists all around the world cheering, because it was the first time a beam of protons made it all the way around that 27 kilometers. So these two dots you're looking at is one of them leaving the detector, and it goes all the way around 27 kilometers, and it comes back the other side. So it showed that the accelerator was working, and it was a huge achievement after decades of construction. Everybody was very happy until the magnet broke. So we had what's called a quench. So I've mentioned that these accelerators are superconducting. They're at 1.9 Kelvin. I didn't really mention what that meant. It meant that at this very cold temperature, it has no electrical resistance. And so we can put 12,000 amps through this magnet, and there's no electrical resistance. But with this one magnet, there was a solder inside of it that had a small electrical fault, and it caused just the tiniest of sparks, which just warmed up that location just a tiny amount. But what it did is it meant that part of the magnet was no longer superconducting, and suddenly there was 12,000 amps going through it. And so that was enough power to physically move part of the accelerator by about half a meter. And unfortunately, that stopped us for about a year, because then we had to warm up the whole of the underground. We had to remove this magnet, replace it with another one, And then we had to go around and check every single solder connection to make sure none of them had a fault, which was a huge endeavor. It took a whole year. And I know some grad students that were waiting for data that had to work a whole extra year because of this, which is unfortunate. But science is tricky, that's why we do it. So in a year later, we had first collisions in the Large Hadron Collider. And we're not known for being particularly artistic, so this is what we saw when those first collisions happened, but this was exciting. These were protons colliding in the center of our detector, and it meant for data analysts, people who analyze the data, the real work started for us. One of the other highlights before I move on to that, though, is that now, as we ramped up the energy over the next few months, the LHC became the highest energy particle accelerator in the world. And so Fermilab, that used to hold the record with the Tevatron, physically passed on the baton at a conference to say congratulations to the Large Hadron Collider with the new record, which I think is a really nice sense of community that they marked the occasion. Okay, and then now we jump to 2012, so after a lot of work later. We had this is the collection of those collisions in the Atlas detector. And we're looking here at 2 photons. And so we're collecting photons. And generally, we expect it to just fall as we increase the mass of the photons. But what we found was the tiniest of bumps at a mass range. And we combined this with some of the other different ways that we thought the Higgs boson would show up. And all of them had the bump at the same point, 125 GeV, which then made this room of scientists cheer. So it was a momentous occasion. This was 50 years of work from when it was first theorized to building the Large Hadron Collider, to analyzing the data, to building the detectors, and being able to say that there was a new elementary particle that had been discovered. For me, I was a grad student, so that's my face. So this is the New York Times, and yeah, this is my face over here. I'm a few pixels. I sent this to my dad. Oh, thanks. That's very kind. I hadn't worked on the Higgs yet. I did nothing for this. But I sent it to my dad, and I said, this is probably the only time I'm getting on the front cover of the New York Times, so please enjoy it. To be in this room, I slept outside the auditorium with some friends. So we turned up at midnight like it was a rock concert that we wanted tickets for. We watched Disney movies, had popcorn, stayed up all night, and at 7 a.m. they let us into the auditorium. So I look more awake than I felt at that point. I had a little nap on the table for an hour before the presentation started. And so this was my view of the presentation. And this is now the Director General of CERN. At the time, she was a spokesperson for Atlas, giving what is arguably the ugliest, most important presentation that we've ever had. Her choice of color scheme is questionable, but the physics is all very important. It also, interestingly, Comic Sans was trending on Twitter that day. But it was such an important moment to be in that room and to see everybody come together and feel the excitement from the discovery. And so now we can show the standard model with the Higgs boson in. And so I hope I get a bit of the sense of the sort of monumentous moment that this discovery involved by being able to add it to our standard model. But we don't rest because there's still a bunch of things missing. So we still don't have dark matter. We still don't know what dark energy is. Gravity's still not in there. So we don't sit down and say, job done. We keep searching. So here are just some of the searches for new particles. And I realize that this plot is a little bit scary. So today, I made it prettier. What I really want to get across with this is that each one of these is sort of 10, 30 people in a team analyzing data for 2 years to look for a new type of particle. And then unfortunately, each one of these, everybody has to stand up and say, we didn't find one. But we do keep very busy. So these are all the different ways that we looked for new particles. And the further along this line is, the more massive we can rule it out from. So even up to 10 TeV, which is a very, very massive particle, we can rule out a bunch of these particles that they don't exist at that mass range. So we can never say that something doesn't exist in particle physics. We can just rule it out up to a certain mass. So we kept very busy. But it's not just about searching for new particles. It's also about precision. So something that doesn't get talked about quite as much with CERN is that we're not just searching for new particles. We've got a whole bunch that we want to understand even better. And by understanding them even better, we learn more about our universe, but it also potentially helps us find those new particles through indirect means. If something is different from our prediction, that's a huge hint that there's something that we should be looking at in more detail. So these are all of the precision measurements, or a bunch of the precision measurements we do in Atlas. I didn't make this one pretty, sorry, but the main thing that I wanted to say about it is that as you go down, so as you get down here in our graph, the processes get more and more rare. So this is 15 orders of magnitude in terms of like how likely a process is to be created in our accelerator. So these ones up here are incredibly likely to be produced, and these ones down here are incredibly rare. And it's the rare ones that we're still interested in. I mean, we are interested in studying all of them, but these ones are difficult to produce, difficult to analyze, and it could be that something new is hiding in these results. So we need more data in order to be able to have enough statistics to look at them in more detail. So one that I'm going to talk about a bit more in detail is the Higgs boson. So we've discovered it. Some people say, OK, job done, you can rest. But no, we've got this brand new particle that nobody's ever seen before. So we're going to study it in as much detail as possible. So here are all the different ways that it changes into different particles. And we're looking at its mass. And the closer it is to this red line, this is sort of the accepted mass that we have measured so far. So this one being outside of that line, that's fine. That happens in statistics, because we can see that these bars are quite broad. But what it shows us is a lot of these yellow boxes are telling us that we need more statistics because they're quite far apart. And so by collecting more data with the Large Hadron Collider, we can make these boxes smaller. And if this one stays where it is, and we squeeze it like this, then it starts to become interesting. It might not. It could move closer to this line. But that's what we want to do. We want to collect more data and see where these points move compared to the other ones and see if anything looks a bit weird. And a bit weird is the best thing you can find in science. So we want to do mass measurements. And one of the reasons that we want to do the mass measurements is it's pretty important to know how stable our universe is. And this is a measurement that feeds into that understanding. So just to explain a little bit, I showed you at the very beginning this, the Higgs, where it fell down into that well. Well, it could be that that well is not the most ideal point. It could be that there's another well further off at a different point. And if that's true, then it could be that the Higgs field might quantum tunnel over to it at some point. And that would change the properties of the Higgs field and the particles as we know it, and it's what's called vacuum decay. So it's kind of important to know if this is going to happen. I do want to point out very clearly, measuring the Higgs boson cannot cause this. We are not affecting the Higgs potential. There are higher energy collisions happening outside in our universe by much, much higher orders of magnitude, but we just want to measure the properties. So instability means that it drops down a lot. Metastability means that there's another well off to the side. And it's also linked to the top mass. I don't really talk about that today, but as someone who studies the top quark, I couldn't help but put it in because there's lots of nice, interesting results about the top mass. And so by looking at these two values, we can kind of see where we are on this field, and we kind of want to be somewhere in the green region. But even if we're in the yellow region, it's longer than the lifetime of the universe. So I really wouldn't let this keep you up at night when there are much more important things we could be worrying about. But it's an interesting thing to measure. Also, potentially, if dark matter is something that interacts with the Higgs field, that would also move this point somewhere else on the graph. So discovering dark matter will also help us to understand how stable our universe is. There's also measurements of how particles interact with the Higgs. So as I said, we want to know these precision measurements. So these are the ones that we've measured so far. This graph is showing us for different particle masses how likely they are to, how strong the coupling is with the Higgs boson. And essentially, we assume that the more massive a particle is, the more it's interacted with the Higgs field. This is what I showed you with the skiing videos. And so far, what we've seen is all these points sit pretty nicely on this red line, and that red line is our prediction. So everything so far is looking pretty standard model. But it could be that when we've only measured these particles so far, the green ones, we haven't even touched the first generation. So we don't know yet if the first generation of particles interacts. We haven't confirmed that they get their mass from the Higgs field, and we don't know if it's at the same rate that our model predicts. So this is something that we want to measure just to confirm and be able to check whether the theory and the data match each other. And also, as I said, maybe there's some dark matter here on this plot as well. So that would be quite an interesting thing if it's a particle, if it gets its mass from the Higgs field, to see if it's interfering with any of these measurements. And so I talked to you about the stability of the universe, and something that we really want to study is how the Higgs field and the Higgs boson interacts with itself. This is one of the next big measurements that we want to do with the Large Hadron Collider. So for example, we want to know how this slope looks. And at the moment, all we can really measure is inside this tiny box down here. This is our current understanding of the Higgs field. But as we improve with our data, improve with our measurements, we get a better understanding of the slopes of these lines. And it can tell us about the early universe, and it can tell us about the future of our universe. So by measuring how the Higgs interacts with itself, it tells us how our universe is going to evolve. So it's a pretty important measurement that we'd really like to be able to do, but we need more data. Now I have a quick aside, because that was a lot of results all at once. So I want to have a side note, which was on the 29th of April, 2016, the LHC experienced a power cut due to a short circuit. And I'm not sure if anybody heard of the cause, but it was a pine marten, which is also a type of weasel. And just for legal reasons, this is an illustrative purpose. Please don't come at me and tell me we've got giant weasels running through the tunnels. But it didn't just happen once, it actually happened twice. But also, again, I say this is illustrative purposes because they're not running through the underground tunnel, they're chewing cables above ground. But it kind of, I say humanizes their weasels, but it kind of brings it that even the most powerful machine that we've ever built can be stopped by a couple of weasels that mistake a power cable for food. And you have to give credit to The Guardian for the pun, Large Hadron Collider on pause, as creature chews through wiring. So they're very good with their puns. Okay, now I'm going to whiz through a couple of the other things that we've measured with the detectors, but I cannot mention everything. Something I want to really emphasize is that you often hear about the Large Hadron Collider and the experiments like the ATLAS experiment. But the ATLAS experiment is really thousands of experiments done by multiple different teams using the same equipment. So it's really not possible to cover everything that we've been measuring, but I really wanted to emphasize that there's so much going on that we don't always get to talk about in the news. But some of the things I want to emphasize, so I touched upon it, but Alice is really doing a big study of the early universe with this quark gluon plasma. So we create these momentary collections of quark gluon soup, similar to the conditions of the early universe. And we're really learning a lot about how this matter evolved, and that tells us how the early universe evolved as it expanded in the very early seconds. The LHCb experiment, we create these sort of exotic forms of matter in the collisions. So the protons that I was talking about earlier, they have 3 main quarks inside of them. That's how they're constructed. But we have these exotic forms of matter that are produced where they have 4 quarks, and even, oh, that one still has 4, but there's 5 quarks as well in some of them. And it's not clear whether they're 1 particle with 5 quarks or whether they're 2 particles in a very tightly bound state. But it's a really interesting process to create them in very short amounts of time and study how these particles can be held together in different ways. So the pentaquarks and the tetraquarks, the sort of confirmation of these was a really important discovery as well. And I also want to tell you, we've got an antimatter factory at CERN. That's genuinely what it's called. This is a sign outside the building at CERN. You can come and get a selfie with it. So very quickly, in this facility, we take some of those protons from the SPS before they hit the Large Hadron Collider. We collide them with the target, and we get antiprotons from that. We can then steer them into the facility. We get positrons, the antimatter version of electrons. We can make antihydrogen, and then we can study how this antimatter evolves. So not just where did it all go in the early universe, but does it have the same properties apart from this opposite charge that regular matter does? And so there's many different experiments in the antimatter factory that measures these properties, and very recently we were able to confirm that, unfortunately, we don't have anti-gravity. So the antimatter falls at the same rate, it seems, as regular matter does. So it's very incredible that we were able to collect enough of this antimatter, hold it in a trap, and then drop it and measure the rate of the fall of gravity, which is just one of the other types of experiments we're doing at CERN. And then also, again, I said some of this is very biased, so some of my colleagues were deeply involved in this analysis, and it was part of a group that I used to run. And so we had the highest energy observation of quantum entanglement of top quarks in the Large Hadron Collider, so in the ATLAS experiment. And so this result was very new. It came out last year, and it sort of opens up the LHC as a quantum factory to be able to study the quantum properties of the entanglement of particles as well. So this is another result that came out very recently that I could talk to you for a whole hour about, but I won't. OK, so one last topic before I wrap up is you might have sat here and been like, that's great, Clara, love it. How does it affect me? Why should I really care that you're doing all of these measurements? I mean, the first thing I would say is learning more about our universe is just a fundamental human curiosity, and it's part of what makes us human, as well as we make art, we dance, we make music, and we should be curious as well. So personally, for me, that's enough of a reason. But let's talk about some of the cool tech that comes from it too. So just to touch on a few things that comes from this kind of technology. So I say doing difficult things gives us better technology that improves our lives and tells us interesting things right now. So for example, there's medical technology that comes from the type of research that we're doing at CERN. So PET scanners are, they owe their existence to the fact that we understand antimatter. The detectors that I worked on for my PhD are now often used inside the PET scanners to more accurately map where the particles have gone. The superconducting magnets, so the fact that they were driven, the magnet technology was driven at previous accelerators, means that we have we have PET scanners, we have MRIs, we have other medical facilities that use this kind of technology. There's Hadron therapy that uses protons in order to treat cancer better. So there's lots of medical technology. There's also lots of cool stuff we can learn about art. So this is Van Gogh's A Patch of Grass. So this is one of his famous paintings. And we can use synchrotron radiation-based X-ray fluorescent elemental mapping. I wrote that on the slide, so I said it right. And we can look inside the painting at some of the previous. So he was well known for reusing his canvases. And without damaging the original masterpiece, we can look inside, and we saw that there was a portrait. I say we, I did not do this. Scientists in general were able to see that there was a portrait he painted underneath this masterpiece. So we can use the same technology, the particle accelerators that are developed for the fundamental research, also to understand history and learn about the process of Van Gogh in his artwork. We can use it to look inside of pyramids without having to break them open. So we can use the fact that muons travel through detectors, travel through any material and are very rarely deflected. We can put muon detectors underneath the pyramids, and then we can see hidden chambers inside of pyramids without damaging them, without disturbing them. So we can learn a lot more about history through that as well. So now I'm going to take you to the future. Again, disclaimer, virtually. I don't have a time machine, sorry. We often upgrade our detector. So this was an upgrade that we did in the last long shutdown of the Large Hadron Collider. So this was a new muon spectrometer that we installed into our Atlas detector. But we're also going to have a much longer shutdown period where we upgrade the accelerator in more detail in order to more compactly, to make the protons even more close together and get even more data in our collisions. So just to show you, this is the schedule for the Large Hadron Collider, and we're here. So we have a lot further to go. We're in the middle of what we call run 3, and we're hoping to go up until about 2040. And during this long shutdown in a few years, we're going to make a number of changes to the Large Hadron Collider that's going to make it an even more efficient machine. So then for people like me who want to analyze the data, we have the challenge that there's going to be even more collisions at once. So I didn't tell you before, but we get on average about 60 collisions every time the protons cross each other. And once we've done this upgrade, we're going to get 200 collisions every time they cross each other. And each one of these collisions makes a spray of particles that goes through our detector, so it makes it very challenging. But as I've shown in some of the other plots, we need that more data, that extra data, in order to be able to look at the very rare processes. And then in the much further future, we are discussing right now what's next after the Large Hadron Collider. So hopefully it runs till about 2040, but after that we've been discussing potential new accelerators that could be built after it. So there are a bunch of proposals. These are just a couple that are proposed for CERN. There are other ones around the world too. So there's discussion about building a 91-kilometer accelerator, starting with electron positrons, because they're more precise. So they can help us to really precisely measure the Higgs boson, for example, and the other particles that we've discovered, and any potential new particles that show up in the next sort of 15 years. But there's also a linear collider that's been proposed. And after this electron-positron, then it's proposed that potentially we could switch to hadrons again this is called the Future Circular Collider. We'd need a better name if it actually got built. And then this could go up to potentially around 100 TeV of collision energy, and this would enable us to look even further at potential new particles that might exist in our universe. And so one of the challenges we have is that we don't currently have the magnet technology to build an accelerator this big, but that was exactly the situation we were in when the LHC was proposed in the 80s. We wanted to build this 27-kilometer-long accelerator, and we didn't have the magnet technology, and so it drove the production of that kind of technology when the LHC was confirmed. And then also, there are other types of accelerators like muon colliders or what's called plasma wake field acceleration, which is super interesting research, and again, I don't have time to go into. So this is a current discussion that's happening now in the community. You might start to hear about it in the news, because as a global community of thousands of physicists, and also more broadly with people who are interested in science, and the people that, we get a lot of our funding from public funding, so we also want to make sure that as a global society, we're making the right decision for the future of science. So you might start to hear more about these discussions over the next couple of years. So thank you very much for joining me.
Thank you so much, Clara, for that fantastic talk. All right, so we'll have some time now to take some questions from those in the theater, and we're monitoring the questions online. So for the Q&A session, there's a microphone that's located there on the stairs. So if you have a question, please make your way to the microphone. If you're unable to get to the microphone, please raise your hand and we will try to get a microphone to you. For the Q&A session for this talk, we're asking kindly, because I'm guessing that we're going to have lots of questions. I've already seen a lot rolling in online. Please only ask one question, if you have more than one question, never fear. Our speaker, and we have other scientists who will be able to answer additional questions in the atrium following the talk. So we would also particularly encourage young members of the audience, students or even high school students, college students, please come down and ask your questions. While people are making their way to the microphone, we have several online questions. So someone asks, what do we learn from human-built particle accelerators that is different from high-energy particles that we detect coming from the universe?
That's a great question. So it's really important that we also study any collisions that are happening out in space, and we have fantastic satellites and telescopes that we've launched out into space. But it's an uncontrolled environment. We're waiting for these particles to come to us and to understand what might have happened out in the cosmos. Whereas the human-built Large Hadron Collider and other accelerator facilities, we control the environment. So we control the types of particles we're colliding, we control the energy, and also we can have it at a much higher rate than what's happening out in the universe. So there are collisions that happen in our atmosphere that are much higher energy than what we have in the Large Hadron Collider. But we have, as I say, this very controlled environment that we surround by a detector that we've custom built for this situation. And so we just have a lot more control over what's going on. And then we create simulations and we can compare that to our data.
Awesome. All right, a question from the audience.
I was wondering about how you say there's these energy collisions and particle spray. Does that make a mess? Have you created some sort of technology to prevent that from damaging other stuff? How does that kind of work?
Yeah, that's a great question. So when the protons collide together and we get this spray of particles that come off, they actually are just absorbed in our detector. So often they release electrons in the detector, and then these just are carried away by the detector. The big challenge is actually, as I said, that we've got lots of hydrogen, and sometimes we are done with the LHC beam, and then we want to get rid of that and then fill a new one in so that it's much more, it's much quicker to be able to have a higher intensity beam. And so that's quite a tricky process to take this incredibly highly energetic beam of protons. And so we have a system that's rigged up with some special magnets that we push the protons into these magnets, they fire it off in a different direction, and then it slams into a block of graphite. And we also spray it around so that it doesn't all go in one point. And it's quite a challenge, and that's the part of CERN that is the most radioactive. I would not. It takes about 10 years. They put it somewhere safe underground, and then it's good. But it gets quite radioactive because we slam loads of particles into it.
Very cool. Thank you.
Thank you.
That's a great question. All right. Other questions from the audience? I think we have Evan can bring a mic if you can't get to the microphone. So please do raise your hand, Evan. We'll look out for you. Okay. Another question from online. Let's see. Wow. How do we know that neutrinos are not the vast majority of dark matter?
That's a great question. It's slightly outside of my wheelhouse because it's more of a cosmological question, but it's just not enough mass, as I understand it. So it was proposed that neutrinos could be a type of dark matter, but it can't account for all of the mass, and I think I'm going to look at some of the cosmologists in the audience, that there's other properties of dark matter that we've observed. It's sort of the evolution of the early universe. It can't account for that as well. Oh,
great. Okay, more from the audience.
Hey, thank you so much. It was a really great talk. I'm curious about one thing in particular. I was wondering what the difference between a scalar boson and a vector boson is. I saw that the Higgs was a scalar and the other one seemed like vectors, and I didn't know what that meant. Thank you very much.
Thanks. Yeah, that's a great question. So it's to do with the spin. So I didn't really go into the spin so much, but the Higgs is spin 0, and the other particles are spin 1. So bosons have an integer spin, but the Higgs boson has a different quantum number than the other ones.
Awesome, thank you.
All right, next question.
Something I've always wondered about particle accelerators. My understanding with relativity is that when things approach the speed of light, they get heavier. So I understand that a proton is light compared to us, but you mentioned that it's a heavy particle on the scale of particles. So as it approaches the speed of light, on a relative scale, how heavy is it becoming? Is there a way to determine that?
So it's a good question, and it kind of is, it depends on your definition. So we often say that it gets heavier, but really it's because the energy it gets from going faster can be, mass and energy are equivalent, like E equals mc squared, so we often compare the two. But really, when we talk about the particles going around the LHC, we just talk about their energy. So it doesn't really, but it is also why massive particles cannot go at the speed of light. So we have this sort of fundamental limit that we can just keep putting more energy in, but they don't go any faster.
Thank you.
Thanks.
All right.
Hi. I was wondering, you were talking earlier about like having like an antiparticle, like a positron and an electron, and that when they interact, they just annihilate each other. So like, why aren't we all light, and why are we here in the first place?
That is such a great question, and we're working on it. But if you have plans to be a physicist, please come join us, because it's one of the big mysteries. We don't know. We see some slight differences. So we look at the processes where you have particles that can change into antimatter versions and then matter versions, and they kind of oscillate between the two. And we see some slight differences and a preference for matter, but it's nowhere near enough to account for all of the missing antimatter in our universe. So we're still trying to study what happened in the very early universe that meant slightly more matter was left over, but it's one of the big questions that we still have, and so we don't know.
Cool,
Thanks.
Question. All right, go ahead.
Well, thank you, Dr. Nellist, and thanks for the fascinating lectures. And I always know that the CERN is a very special place, and I actually been there once myself, and I had the tour, and so for tonight's lecture, I think I know it is a very special one, and I actually wear the T-shirt from CERN and standard model on it in your honor.
Thank you.
Okay, here comes a question. Last time I visited CERN, and all I can do is just to visit the visitor center and the exhibits, of course. But I would love to have the opportunity to go down to see the experiment, the equipment, the 100 meters, below. But is it possible that I know there's a lot of reasons that are not open to the public, but then say for enthusiasts or aficionados like myself, perhaps maybe someday when CERN is like for any occasion, some occasion that it shut down and allow people to go down to see the real stuff.
Yeah, so
I would like to be the first one to sign up.
So yeah, I mean, I have a friend called Robin Ince who's a comedian in the UK, and we took him underground, and he compared it to seeing Stonehenge in terms of sort of the awe of this giant machine. So I understand the desire to come underground, and we'd love to take as many people as possible. When we're running, of course, we can't take people underground because of the radiation. And when we're shut down over the winter, we do have limited tours, but they're really only a few of them, so it's difficult to have them completely open to the public. But we have these open weekends during the long shutdown. So the last one was about 4 or 5 years ago, and the next long shutdown that we have, we'll hopefully have another of these big weekends where we open up every underground site, and that's the best opportunity to come underground because we have all the experiments in the LHC, and it's really a number of different underground tours. So I would keep an eye out for that, because if you're going to travel a long way, then you want to make sure you go
Can I
underground.
leave my name?
You can follow along on the visits.cern website, and we will definitely announce it when it happens.
Great, thank you so
Yeah,
much.
thank you.
Everyone can mark their calendars.
Yeah.
All right, next question.
Thank you for your presentation. I'm wondering, when these protons hit each other and you get this spray, does the sprays have a pattern? I'm sorry, I'm not an experimentalist, so they have a pattern that you recognize, oh, that's this element. And were you or scientists able to predict, if we see a Higgs boson, it's going to look like this. And if we see a dark matter particle, it probably is going to look like that, a spiral, a zigzag, whatever it is. Are the theories there for you as an experimentalist to look for?
Yeah, exactly. So that's a really great description, because each different type of particle, so for example, the Higgs boson can change into about 5 or 6 different types of particles, and each of those has a different signature in our detector, and it also depends at what energy they're created at. So we can predict all of these distributions, how they look in our detector, and we can never say that an individual event definitely had a Higgs boson in it, but we collect them all up and look at the frequency of each different one, and then we can see that, for example, we get twice as much of one type as another, and then that's probably because of a Higgs boson. And so we do the same with dark matter. We can predict, so theorists come up with ways that dark matter should change into regular matter, because that's one of the easiest ways that we could see it, or if it's missing from our detector. And then we look for those signatures in our detector. So we look for the very specific signatures that tell us it was a type of particle.
So you're looking for the things that the Higgs boson will turn into.
Exactly. We've never measured a Higgs boson, only what it's changed into.
All right, so you don't see a line particularly for the Higgs boson, or?
No, it's too short-lived. So it's created in the collisions, and then it quickly changes into something else.
Let's see. Okay, thank you.
Thank you.
All right, we have time for 3 more questions, just so happens.
Sorry, you were talking about antimatter and how you can like make it in a factory. I was just curious, like what makes antimatter sort of different from like, I guess, regular matter, you could say, and what makes them sort of annihilate each other? Like, why don't they like each other?
Yeah, so the big difference between matter and antimatter is that they have opposite electrical charge. So for the electron, the antimatter counterpart is a positron, and it's a positive electron. The electron has negative charge, the positron has positive charge, but otherwise their mass is the same, and that picture that I showed on the slide, it looks exactly like how an electron would behave in the setup, but it bends in the opposite way in the magnetic field. So they're very similar, and it could have been in the early universe that actually more antimatter was left over, and as far as we know, we'd look exactly the same. Our antimatter versions would, as we assume, look exactly the same as us. But if you come across an antimatter version of yourself, please don't high five, because that's when the annihilation happens.
That's interesting, because I'm in grade 12 physics right now, and we talk about how like a proton has the same charge as an electron, but it's just opposite. So like, why can't they annihilate each other?
Because they have different quantum properties otherwise. But yeah, we actually also don't know why the proton has the same but opposite electrical charge as the electron. That's just one of the quirks of the universe.
Okay, cool. Thank you so much.
Thank you.
Hi, I was wondering, since the protons are so small, like, how did people figure out how to align like a super, super small beam to make sure there were collisions happening?
Yeah, that's a fantastic question, because it's the whole engineering and the accelerator research side that I think doesn't get talked about enough, because it was a huge challenge in order to be able to get these protons. We don't have individual protons. I don't think I said I meant to. We have 100 billion protons in each bunch. So each bunch of protons has 100 billion inside of them, and then we use these strong dipole magnets that are superconducting in order to bend them around the ring. But we also have higher order magnets that squish them together. So we use the higher order magnets to focus them, and then we can see that charge inside the accelerator to kind of know where it's gone, and then the technology keeps it on track. And the width of this 100 billion proton bunch is about the width of a human hair. So imagine trying to fire 2 human hairs at each other around a 27-kilometer ring and get them to accurately hit every single time. It's a huge challenge.
Thank you very much.
Thanks.
All right, final question from the audience.
Hi. You talked about the streaming and the filtering and the storage of all that data that comes from a detector like Atlas, and also about the upgrades that happen over time. So between 2008 and now, there have been a lot of advancements and increases in processing power. Are things like that, is that part of the system sort of upgraded over time, like every few years, as opposed to the big physical parts that are upgraded every decade or so?
Yeah, I'm glad you asked, because again, this is one part I don't think gets talked about quite as much. There's a lot of technological advances that we implement into our data selection. We're getting better also at deciding which events to keep, because I mean, also we don't want to keep them all because it's petabytes of data. So I almost put in, but I was trying to stick to time. But there's a graph we've got showing if you just kept all the raw data from the Large Hadron Collider, then it's more than all of YouTube, all of like Microsoft's storage, and it's a significant amount of data. So we don't even want to keep that because it's too expensive to store it all. But the advances in processing, so computers have gotten better at processing. We're also, again, something I wanted to put in, but for time, I didn't talk all about the machine learning that we're doing. So we're not only using machine learning, but we're driving machine learning development. And so we're implementing a bunch of that in sort of the firmware, the hardware that we're using to make the selection. So I think LHCb is the one that's currently, they've implemented machine learning algorithms to make that decision within their hardware. And so we're using these technological advances to make better decisions. But also, because we know we're not perfect, we're not arrogant enough to think we're doing the best job ever, we keep a random subsection of the data and just say, just in case, we'll randomly keep a bunch too, and then later, if we realize that we could have done it a better way, we can look at that data set and see if we were missing dark matter all along in that data set. Thanks.
It's a great question. All right, so thank you to our online audience, our in-person audience for all of your great questions. Please join me in thanking again Clara Nellist. You're welcome.